Get some of the high points, so let's get started. I am Martin McClure. I work on the design and the implementation of various of the products for GemTalk, the GemStone S line of products.
And I'm Andres.valloud, and I write virtual machines at Labware.
Okay, well, Andres, why don't you tell us a little bit about why you might want a hashed collection?
The thing with data, right? Because like a very long time ago, we had no memory, so who cares, about data structures? In our search through your 256 bytes of memory you have. But unfortunately, eventually, poorly in our search, complexity n grows large. So here comes some other one that says, hey, if you keep the list sorted, at least you can cut down to logarithm of n, and that's great. But eventually, even logarithm of n is too much. Let's say that n is, the logarithm is 30. Oh, so you mean your latency is 30. So 30 disk accesses, 30 memory accesses, etc. And these days 40 some. And so wouldn't it be nice to have O of 1, right? Because those other functions here, they have n in them, but how about no n? And do you think such a thing? Maybe, huh?
You think there is such a thing?
No. I don't know.
Do you believe? Do you believe?
Right? No n. Right? Well, make this as big as you want. Whatever. Make it the entire size of the universe.
Yes. Something that no matter how big it gets, the search takes the same amount of time.
Oh, no matter. What do you think? No, huh?
Well, there is such a thing, and it is a hash table. So, what is a hash table? So, we have, we're going to make an address book. So we've got some contact objects here, and we want to store them. And we want to store them in a way that we can look them up. And so we're going to look them up by name, and we're going to call the names of these contact objects the keys. Okay. And we're going to make this thing that we're going to call a hash table, which is basically an array or something like an array. And now we have to go, in order to do this search in constant time, where are we going to store these keys in this hash table array? Well, in order to figure out where to put them, we have a hash function that maps from a name through some kind of arithmetic computation into an index into the hash table. So we'll get into much later as to what that looks like. But so Andres is going to hash to 8, and so we put his contact object there, and Dale will hash to 4, and we'll put his contact there, and we will hash James to 2, and we will hash Norm to 11, and there we go. So now we have a hash table. And we've stored these things through some function. So now when we go to look them up, we perform the same function on the name we're trying to look up, and it tells us which slot in the table to look at. And there we go, we've found it. So you might ask, why the name hash? Well, one of the meanings of hash in English is to chop and mix, and that isn't exactly what a hash function does, is it takes the items you have and just sort of mixes them up in a way that if you're really lucky, it looks like randomness, and or if you're really clever, it looks like randomness. And so this term has been in use since about the 1960s in computer science, but before that, this is what hash meant. Chopped and mixed. So, there you go. It's pretty simple, right? Well, okay, it's not quite that simple. That's not the end of our talk? Okay. Okay, so what hash...
We're in the spirit of moving along, right? So,
what do we have in Smalltalk?
So, typically, this should be pretty common to everybody, that we can have things like a set. Let's say it's a particular type of hash table. You can have key objects, and you can put them inside, and all sorts of things with that. Once you have them there, you can ask nice questions. It's like, do you include K, right? And each time you do such a thing, you're invoking the O of 1 complexity that we're talking about. And in this case, it includes K. Says, yes, true. the funny thing, though, is that a set, everybody knows, right? A set goes by equality, right? So equal things, it throws them out because there's no duplicates. And so if you have a K of a different color this time, it still says true. Even though the thing it has in it might be black. This would be like a representation of two instances of the string, tick, K, tick. And so since they're different, K, that one is still included because there's a representative that's equal to that one still in the set. And add works in a similar way. So for example, if you have this time S is in the set, right? So if you add it again, you get the same S again. Because yes, I already had it, but nothing happens the second time. And then, if you take another S that may not be inside, it still gives you the same S that you set to add, but the original one stays in the set. Now, and of course, the other things like reject, select, all this type of thing, and remove, and blah, blah, blah. All the things we're all used to. Now, by the way, that means, the previous slide means that do colon, well, since we had an array thing, right? What a nice way to iterate through an array thing, such as 1, 2, size do, which means that the order of iteration is, well, who knows? It's whatever the hash function says. So there's no determinism there. And of course, now, hey, if we have a set of objects, we can also have a set of associations. And conceptually, that's a dictionary, where each of the keys has associated with some other object. And now instead of add and thank you for the service, Mister. And so, and now you can do things like, hey, give me the thing at S, not the S with a different color, and it still works, and it gives you the blue little object, because dictionaries also go by quality. And you can also do a put where, let's give it this pink thing, and right now it's blue, but after a put, it's going to become pink now, you see? And so on. And these are the basic uses of hash collections in Smalltalk. All of us are familiar with this. But all of this is backed up by hash collections. Now, this is nice. However, maybe, have you seen these hierarchies that go dictionary, identity, weak key, dictionary, weak identity, event queue, hashing reverse, dictionary, maybe?
Oh, I like that one.
That's nasty,
That's good.
I would not want to write that one. But there's use cases here.
I've written it at least 3 times.
No. Okay.
So anyway, so we said that we were going to tell you how to build your own cached collections. And, so there's a question about that, which is why? Right? We've got all these really nice collections already built into Smalltalk that Andres just told you about. Why would you want to build your own? And there's a number of reasons that you might want to build your own, but many times you don't. Many times you just want to use the system ones. A lot of the times people are saying, oh, I want something that's a little faster. It's like, well, profile your application. If the collection is taking less than 10% of the time in your application, then it's probably not worth building a new collection. But, if you're finding 80% of the time in your collection, then you might want something that's faster, or maybe something that's more compact, or whatever. So,
wait, you mean engineering backed up by fact?
Oh, we can't have that. Come on.
That never succeeds, ever.
So, sometimes you have special requirements. We'll see some examples of that later. I've got a dictionary later in this talk that has a key, each key associated with 2 values, and more requirements than that. Security is another topic we'll come back to later. That's become more, with online applications, security has become a more big deal, and the built-in Smalltalk collections do not really offer much security. Performance we just talked about. Performance can be either space, you want something that's more compact, or something that is faster. So, if you're going to build your own, and then you need to know about hash functions and domains.
Right. That wonderful question mark that we saw earlier. Well, what's in that? Well, let's say that we have that data set, right? Now, since all we're looking for is indices into an array, essentially, right? Suppose we have what data set? Suppose we know for a fact there will never be no more contacts than these people. I'm sorry.
These are the only people I know.
Yeah, that's right. Yeah. Those others are not the ones
I
you're
will
looking
never
for.
meet anyone else.
That's right, that's right. You'll be ghosted forever. And except you're with these 4 people. At least it's nice people. So then, right, if you know it's going to be 4 forever, then all you need is 4 indices and you're done. Right? You just make a nice perfect hash function. You throw somehow, I don't even care how, you throw each of these things in your objects that you're going to hash, or are going to be subjected to hashing to some unique index, and you're set, right? Like done. You can even make it nice and make it compact instead of 10. That's a good number, I don't know if you know. But you could make 1, 2, 3, 4, right? The same thing, like you're done. Yes, except everybody knows, if you have a big enough hard drive, you're going to fill it with stuff, and now you're going to have more than 4 contacts. You're going to have something that looks like this, which barely shows. However, if you
might meet that many people.
If you squint a little bit, you're going to see there's an F there, right? And there's an R, and A, C, E, I, and T. That's the name of a really old fractal software, and that's actually a fractal. Each of the edges, it says fractintegrant, and that's how typically data sets look like, or domains. That's what typically hash function domains look like. Let's say for strings, right? And let's keep it simple. Let's say just digits, 0 to 9. What do data sets look like? Well, one of those followed by another one of those, followed by another one of those, and you don't even know sometimes how big they can be. So if you try to enumerate them, count them, you're going to end up essentially with as many values as digits you allow. Well, soon enough, you run into large integers, and horrible things happen there, because try arithmetic there, slow. You don't want that. And so, let's get pragmatic and say, well, yeah, large integers is very nice. We're going to cheat a bit. We're going to let these things get compacted in range, and essentially, one of the most typical arrangements is as you take something and you take some value modulo S for a well-chosen S, and that well-chosen S, of course, is the size of the table. You see? This also shows how hashing is organized in Smalltalk, where what we call a hash function is actually composed of 2 pieces. Right? You have the hash method over there, what is usually called a hash function. Yes, I know, but this is the hash method that provides some value k over there, which then, see, you go from string in this case, via hash, you get some value. And then now you have to put it in this array that it goes from 0 to s minus 1, that's why the s, and you look at this value modulo s, and that's your index. And that's wonderful, and that's typically what's done. Now these hashes, the previous ones were perfect, right? These ones, they're not. And there's a side effect to that. You lose a nice property.
Yes, since we have to deal, when hashes are imperfect, and again, a perfect hash, you have to have a table that is as large as every possible value that you're going to put in it. So, with an imperfect hash, we must deal with collisions.
Bad things happen.
Okay, so let's take a look at how collisions happen. So here we have a 5-slot hash table. This is actually a fairly typical case that, in Pharo, for instance, if you say set new, you get a 5-slot table because it's the default initial value of that.
Yeah, it's also another form of digital method, you see. Yes.
But also a prime number, oddly enough. Or even, no. Okay, it's even a prime number. Okay, how about that? Okay, so we add one key. Our first key hashes to the value of 3, we put it in slot 3. Our second key hashes to the value 1, we put it in slot 1. Our third key hashes to slot 3, we put it in... Okay, so this is a collision.
Yeah,
Boom.
You tried at least, huh?
We tried. Yeah.
Didn't work.
Yeah. So how often does this happen? Well, it turns out that it happens relatively frequently, like a lot.
Always.
So, for a random hash function, and randomization is sort of the ideal for an imperfect hash, usually You measure the quality of a hash function by how closely it approximates a random number generator. You know, you start, yes, the very first one that you put in does not get a collision. Okay, so the axis here is load factor. This is the number of keys over the table size. And then this is the average, how many keys you get per hash value. So, you know, so like here, we're getting like for every, you know, at this load factor, we've got 1.5 keys for every hash value. So there's a bunch of empty slots in the table at that point, but there's a bunch of others trying to crowd into the same. And this is very similar to a thing that's known as the birthday paradox. For instance, in this room, we have far fewer than 365 people. And yet there is about 99+% probability that there are 2 people in this room that have the same birthday. Because the 50% probability comes at 23 people or so. And by the time you get to 50 people, you're almost certain to have 2 people in the room with the same birthday. So that goes up. So you're going to have collisions, and you're going to have them relatively frequently, but you know, you need a way to handle them. So there's 2 basic techniques for handling this kind of a situation where you're trying to put 2 things in the same slot. And one is that you find some way to put multiple keys into the same slot, and the other one is you find another slot that you can use. So there's a thing called buckets. This term is used slightly differently by different people, but this is the technique for putting multiple keys in the same slot. So basically you have this bucket, and you put a key in it, and you put another key in it, and you put some more keys into it, and basically, you know, they're all stuffed in the same bucket. Now, here we have linear search inside of a bucket, because we don't have any indexing, any hashing, or anything within the same bucket. We've all just hashed to a bucket, and if you have put multiple things in the bucket, you have a linear search there. So you don't want to put too many things in the bucket, which is why you want an even distribution to try to, you know, minimize your collisions. There's a couple of ways of implementing these buckets, you know, that you can put multiple things in. You can make it a linked list, like this. You have a bucket in each slot. We're going to make a linked list. So we add our first key, and it goes in. We make a linked list node in 3. And if you remember, our second key hashed to 1. So that was pretty easy. And then our third one, we hashes to 3, and so we insert at the front of the linked list, we insert that key there. So that's really simple to implement. It turns out the code for this is pretty easy. Adding and deleting from the linked list is very easy, etc. But as we will see later, the performance maybe. So another common technique is to use arrays for buckets.
How do you put an elephant in a refrigerator?
With a good hash function? No.
With a large enough bucket. You open the door, you put the elephant in, and you close the door.
That doesn't seem very nice to the elephant.
So let's try with force.
Let's try with So we start. So here we start with 5 empty arrays for our buckets, because each bucket is an array. We put the first one in slot 3 again. We put the second one in slot 1, and the third one we now have a 2-element array where we have added this third element after the first one. So that's kind of, you know, the way you do buckets. The other option is to do what Smalltalk does, most Smalltalks do, which is linear probing. This is the technique for finding a different slot in the table to put things when you find collisions. And it's a pretty good way of doing things. So once again, we have our same thing. We add our first key, it goes in slot 3. The second key goes in slot 1. You notice that now we have a direct reference from the table to our elements. And then we add the third one. And what we've done here is the third one it hashed to 3, but 3 was already occupied. So we've just, the linear part of linear probing is you just go to the next one and you say, is it empty? And if that one was full, you would have gone to this one. Was that one empty? This one empty. So you, and it's also very important never to fill the table all the way full when you're doing this, because then you will be playing an infinite game.
Note also that that means that the third key can be behind slot 3. That can also happen.
So I'm sure that some of you can think of ways to improve various of these schemes. And there's one possible improvement that I thought I'd include today, which is a thing I call lazy buckets. We're trying to get the best of both linear probing and the other bucket methods that I talked about. So with this, we start out just like linear probing. We add directly to the and so then we do that. But when we collide, so it's only when we have a collision, then we make it into an array bucket. So anyway, so this is some of the basic ways of handling collisions. We'll come back to that later and talk about possible ways you might want to think about how to choose which way to do it. But for now, we have for you.
It sounds great, right? It sounds so simple, etc. And the problem is, it's rather easy to not get all the way there. And one of the topics that usually comes up a lot is, well, how to choose a hash function. Well, for now, let's concentrate on the first half of the hash function that we were talking about, the hash methods, right? So let's say that we have here our lovely data set of things we're hashing out of our domain. And let's say that we're getting different values out of the hash method. That seems like it's okay, right? We have the same amount. And obviously, if you have something like this, now you're asking for trouble, right? Because once these guys collide, nothing else, no modulo S, no rehashing, no massaging the bits to see until they change, etc. will fix the fact that now you have 4 collisions, or rather a 4-way collision, because all these keys will want to go to the first slot, inducing linear search, right? Now, in addition, it doesn't even matter that the values are different. You still have to measure, right? Because it may be that, yes, they are different, but guess what? They're all multiples of S. And if the next thing that happens is modulo S, all of those go to 0 and linear searching. And I'm so sorry, but then support gets called, And we'll be on the other side, and yes, it's like, please don't do this, right? It's rough. So, ideally, now mind you, right? This is for simple things, like we have the 4 contacts and such. But in reality, we have the fracting thing that if you squint you can see. And ideally, you would want to take any random string in this black thing into random values modulo S. Because then you get all the properties that you expect from a hash function and from a hashing implementation. What's a good way to do that? A crypto hash. What's a slow way to do that? A crypto hash. So you don't do that because it's very slow.
How do you put a crypto hash in a refrigerator? You have to take the elephant out, right?
Yeah,
exactly.
right. But first you get the key, huh?
First you get the key, yeah.
Sorry. Boy. So, no, right? We're going to get one of these. What, like if you go to Google and put hash function there, not with the agreement that we know that a hash function in the environment we're talking about is the combination of the hash method and whatever the table decides to do, right? With that approach, then with that in mind, you go Google whatever hash function, and now you get, great, it's fast, and great, you get maybe random values modulo S. So now you lost some of the guarantees. And that means that you got a test, right? This is borderline cheating now, and then cheating where you can get caught. Because if this maybe random interacts poorly with your choice of modulo S, for instance, this is bad. And now you get linear search again. And this brings up a lovely topic of, well, what should S be then? Because if it were a crypto hash, hey, look, all the bits can be whatever, they are guaranteed, they are constructed that way, that's great. Now you have all the guarantees in the world to just say, you know what, I'm just going to cut off the bits, use power 2 sizes, I'm done. Right? Because all the bits can change, it's the same, that's one of the guarantees of the crypto hash, that they have no pattern to them. But with this, I'm not so sure, right? Because what happens if maybe they don't get 2S, 3S, 5S, 7S in there, but now you start getting all multiples of 2, and you're still using an S that is a power of 2. Now the bottom bit is 0 all the time. And you get linear search again. And that is bad. And if you get collisions with bigger factors, right now in your histogram, instead of being nice and uniform like this, it's going to be like this. Right? With spikes. And all of those spikes here will have to push them down, right? And then they'll collide with each other. And so they'll push everything, and now everything collides, and it's a complete disaster. So you don't want this to happen. And so if you don't know what this is, because the vast majority of the time, all the guarantees of good behavior that you're going to get out of this is so-and-so wrote it. I tested it on my laptop for 5 minutes and it worked. On a weekend, maybe. Then, at the very least, choose a chosen, make a good choice for a prime number. And there's various ways to do this, and I think in some Smalltalks there's actually a description of what this process is, but that's why it's important. Otherwise you will lose the guarantees on O of 1, and then you'll wonder what happened. But you see, now we have more risk of collisions.
Indeed. So, collisions. Again. So which of those strategies I talked about before should you choose? So let's look and see what might be the things we would look at. So one of the things about speed is, right, if we're going to get collisions and then we're going to have to do a linear search, obviously, right, the more things you have to search, then the slower it's going to be to find a given key. So here we have a graph of, for the load factor, number of keys relative to table size, what's the average number of probes in order to do a lookup? So here, it obviously starts at 1. If you only have one key, then you can look it up and it's going to be the first thing you look at. So number of probes equal to 1. And as the load factor increases, you find more and more things that have had collisions, and occasionally you have to do a second one, and occasionally you have to do a third one, and so on and so forth. And you can see that the number of probes average for the bucket only goes up to 2 probes, even if your loading is two times the size of your hash table. Whereas with linear probing, of course, you can't even reach 100%. Because then it would be full and there would be no empty slots at all, because they're all kind of crowding there into the table. So it goes up like this. So obviously, right, some buckets win, right? Well, maybe not so fast. What if the cost of a probe is not equal between the two approaches? And in fact, that is what we find. And the reason is cache line locality on modern processors. So modern processors have processor caches. The cache line is typically 64 bytes, so you get a 64-byte chunk at the same cost and then anything else is in your level 1 cache, and it's faster to get at. In fact, on the machine on my desk at work, it takes about 1 nanosecond to access a word of memory out of the level 1 cache. So 1 nanosecond, about enough time to execute 10 or 20 instructions. However, getting the same cache line out of main memory takes 60 nanoseconds, enough time to execute 1,000 instructions or so. And there are, level 3 and level 2 caches as well that are different amounts of time and are larger. But that this is this difference in 1 nanosecond and 60 nanosecond is really large. So we come up with this hypothesis.
Also, that pushes people away from your software. If you study, it will.
Yes. So our hypothesis is that the cost may be proportional to the misses in the level 1 cache. Right? If we can execute 1,000 instructions in the time that it takes to get one cache line out of main memory, then maybe the cost of our hash function doesn't matter, maybe the cost of other things, don't matter compared to that. So let's make some predictions based on that. So here's a prediction based on our linked list buckets. You can see it starts at 2 cache misses, and why is that? Well, the structure of this is, first of all, you have to pull in the cache line of your table, of whatever section of your table you're dealing with. Now, this table of 5, right, it's all going to be in the same cache line almost always. But if you're dealing with a table that's 1 million large, then you're probably, there's no reason that it's going to have to be in the cache when you start, so you have to bring in that. And then you have to go to another object, and we're assuming that every object is in a different cache line. So we're going to start by saying, if I want to get to key 2 or key 3, I incur 2 cache line reads, one for the section of the table, one for the linked list object. By the way, this is for an identity set, so we don't actually, in order to do the lookup, we're only looking at the identity pointer. We don't actually have to pull in the object and run the hash method on it, because that just complicates the comparison. But if I want to go and find this key here, then I'm going to take three cache line misses to get that. And so we see that it starts at 2 and goes up gradually after that. So let's look at the array buckets. We see that they also start at 2 and go up, but more slowly. Why is that? Well, same thing. We have to go here, read a cache line, here, read a cache line, done. Here, read a cache line, here, read a cache line, we can get to key 1. But key 3, there's a high probability that both of these are in the same cache line. Therefore, we don't incur a cache line miss if we're reading this one, in most cases. So why are there 3 lines here? Okay. Oh, did it? Okay. Okay. So why are there 3 lines here? This is based on different assumptions based on how many keys you can fit in a cache line. So the upper one is only 4 per cache line, which would mean like 16 bytes per entry, which you might get on a 64-bit system where you have keys and values together in the hash in the buckets. 8, which would be a 64-bit system that's just an entity set, and then this is for a 32-bit system where you can fit 16 in the cache line. And it looks from this graph like that one is completely level and not increasing, but in fact it is increasing just very, very slowly. In fact, here it was at about 2 and 2 millionths when I looked at the actual data set that graph was made from. Okay, let's look at linear probing. Okay, this starts at 1, and it does go up following that curve that we saw before for the number of probes, but it starts at 1, which is much better, right? So why is it only at 1? Well, here we only have to read the table itself to find the key. So here, if I'm hashing, if I'm looking at this one, I get the hash of 1, I read it, I go, yeah, it's identical, so good, done, 1 cache line read. If I'm looking for here, same thing. And if I'm looking for this one, I read this slot and go, that's not it. I have to read again. So I have to do a second probe. But the second probe is usually in the same cache line. And so that's why we have this. Once again, the 3 different lines are the same thing, 4, 8, and 16. And now we've added our lazy buckets, which kind of, as we might expect, start out looking like linear probing, but the more collisions you have, then the more array buckets you create, and eventually you almost fill the table, and it's going to approach the performance of the array buckets as the table size goes to infinity, or the load factor goes to infinity, which you wouldn't want to do anyway. And once again, that's, we see that here. Here it's like a linear probing, and here it's like a hash bucket where you have to do 2 probes to get both of those. So, yes. Go back to here. Yes.
So here, when you remove, what's happening if you remove K1? You put a marker to say that it's invalid?
What happens if you remove K1? There are a number of techniques there which are beyond the scope of this talk because we only have 45 minutes or so. But yes, there are a number of options. In some cases, you would put a marker there, or you would nil it out. There are various strategies for keeping track of where the... I have built one where, because of limitations, the hash buckets get very large, and we actually keep a linked list in the buckets. We keep a linked free list. So you could also move this over to there, which is actually fairly cheap if they're in the same cache line.
This is what you presented at Russia.
What did I present in Russia? I don't remember what I presented. Where's Russia?
Linked weak arrays. This is something different.
No. Oh, linked weak arrays. No, that's different. That's a different. It's related, but tangentially related. Okay, so we have these predictions, which were made by a simulation I wrote in Pharaoh 7, using specially instrumented collections. Now, the range of load factor that we're interested in, I'm going to talk to this half of the audience for a while. Okay, so
Thank you.
So usually we only have this this range that's in the yellow box that we're really interested in, because, like for instance, Pharaoh goes to this point, which is 75% full table. And then basically grows the table to slightly more than double its size, which brings the load factor down to about here. So most of the collections, fall in this range. And you can kind of see why, because they're using linear probing, and linear probing starts to really take off right around that point. And you want the times down here where your number of cache line misses is fairly low. But, this is all the model. This is all based on the hypothesis that cache line misses matter. So it's time to test the hypothesis.
And see, that was not the truth you were looking for.
Yes. I wasn't going to do this originally, and then I wrote all this program to draw all the pretty graphs, and then I went, it's not that much harder to run the timing. So here we go. So this is the actual timings that we got. This gray line at the bottom, that's the overhead of the test. That's using a dummy collection that when you tell it to look up a key, it goes, oh yeah, got it. Just return. So this is the time to actually iterate through all the keys and send the message. So we can kind of subtract that from the line above. And so what predictions did we make that this bears out? Well, it does show that the array buckets and the linked buckets do grow more or less linearly as the load factor increases. It shows that the lazy buckets, the purple line, starts out kind of like linear probing, and then goes and does approach the array bucket line. It does show that linear probing, the brown line, is the fastest. So those are all good predictions. So it shows that the model was worth something. There are some things that were not predicted. Of course, we didn't claim to model everything. Like, why does the time increase per element when the number of elements increases? Why do we get this dip here, which is real and repeatable, and I don't understand it. It's probably something about memory management in Pharaoh. And this interesting dip down here was not predicted. I speculate, without any actual proof, that is the result of some effects of the level 2 and level 3 caching. Because when you get about here, this was about a 1,000,000 element hash table. So as you get about here, you get to a plausible point where you might have saturated your level 3 cache. So maybe that. We also have one complete failure to predict here, which is linked buckets are faster than array buckets by about 30 nanoseconds per lookup. And as you can see from this graph, 30 nanoseconds is a relatively large amount, and relative to the amount of time it takes, because once you subtract out this line, we're doing lookups here in about 20, less than 20 nanoseconds at this point in linear probing. So for it to be 30 nanoseconds faster for something that, I really have very little explanation for this, although Andres had a thought.
As a guess, I did not look at the code, but if I were looking at this in some of the VMs I worked before, I would say, array add is going to have to do bounce checking. And likely the add primitive is one of the add primitives. One second. What, you have a thought?
Yeah, I mean, if this is a test that sequentially allocates links.
Allocates what?
Allocate the links in the linked buckets. Then the allocator will always, you get the same cache location.
They'd be in the same cache line, yes. I neglected to mention that when I ran this test, I randomized the order of the lookups. So even if there is, and I did get different results between that and not. For instance, when I didn't randomize the lookups, the array bucket line was much closer to a straight line all the way down. We didn't get the dip. And then when I randomized it, we do get the dip. But yeah, I tried to eliminate those kinds of factors.
But, thank you. In generally, the add primitive, there's going to be first you need bounce checking. Then you also need to check the header. Is an index object, blah, 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 some primitives do. And usually there's one add primitive. There should be many. But if there is only one add primitive, now the poor add primitive has to start asking questions like, is this a byte object? Because if it is, I have to treat the index one way. Is this a pointer object? Because if it is, I have to blah, blah, blah. Is this a big object? And now I have to check whether the size is large in an overflow field, perhaps behind the object, blah, blah, blah. And with an instance variable access, you get nothing. It's immediate dereference with an offset. Done.
So maybe.
It's a guess.
So maybe. So, okay, and once again, this is the area of interest. And there's, so I think what we've shown is models help. Understanding what you're doing helping, but they're not infallible. You need to test. This is just for lookups. Maybe you add a lot, maybe you delete a lot. Maybe in a lot of applications you just add a bunch of things and then you do a zillion lookups. Sometimes, maybe you add 5 million things and then you only look at 5,000 of them and throw the table away. Then you would be testing for different things. But yeah, so basically test your predictions. Test things. Don't trust things you read, especially on the internet. Don't trust us. No, test your assumptions. Okay, so we've used very nearly 45 minutes. We've got more. Do you want us to keep going?
I heard one, yeah. I don't hear any no's. More yeses over there.
Okay, I think, so we've, voter turnout is low, but it is in the positive, I think. So the motion carries. All right. Let's get on with it and see if we can whip through the last stuff in less than 2 hours. Okay, security.
Well, no, we already slide, 113 out of 3,000. All right, so security, and you wonder why security? Well, because, look, check this out. Now that you know how this mechanism works, and now that you lost some of the guarantees, of the theoretical guarantees of crypto hashes, etc., you can abuse. Because why wouldn't you, right? And here's a nice way you can abuse. Remember this? All right, this quote hash function unquote, and we know what that means. And it goes to maybe random. Well, because it's maybe random, maybe I can put this in, and now you get fixed values modulus, and your performance stinks. Becomes linear search. You don't want this to happen to you. And so, there are, however, theoretical approaches around this problem. One of them is SIP hash, in which even if someone outside of your running system knows you're using SIP hash, and knows what keys have been fed to SIP hash, and even knows what values, apparently, as I read it, what values SIP hash has produced before, they still cannot tell what value is going to come next. And now, this is avoided with these type of theoretical approaches. So, see, this can be avoided and it's not that hard. So, watch out, don't fall for that.
Right, yeah, so if you have anything that's like exposed on a web app or something where an attacker could choose the keys that are going into your hash table, and this is a real problem out there. It's known as a hash flooding attack, and all sorts of languages are changing their hashing structures in order to get around it.
So, right? So this means you got to test. You got to test, and you have to work around this shortcomings of theory.
Right.
Because at least, right, SIP hash apparently is not as computing heavy as a crypto hash, so that's why the advantage, because otherwise, crypto hash, right? But that means that now you don't have all the guarantees you want, so now you got to test. And that so-and-so wrote it is not a guarantee.
Right. It's easy to get hashing really, really terribly wrong. So, some examples. Java 1.0, the string hash.
Wow.
It hashes the first few characters of the string and the last few characters of the string and ignores the middle of the string. Alright, now when they wrote the Java 1.0 language specification, they thought they had it good. They thought they were never going to have to change it. They changed it. They changed it in one way. They changed the hash function to hash all of the characters. Because it turns out, what were people using hash for in the mid-90s? They were using it for web applications. What are they hashing? They're hashing URLs. What do all URLs start with? HTTP://. What do all URLs end with? .html. It's totally terrible performance. So, of course, they fixed it. But...
hang on. Before you laugh too much, watch out, because Squeak had the same problem. VisualWorks had the same problem. Who fixed that? And Luciano Francesco. Credit goes where credit should go. And also Michael van der Gulik. But, so, watch out, right? Don't think too highly, because immediately you get complacency, and that's like number one requirement to get things wrong, complacency. Think you got it right. But you think Java 1.0 had problems? Here we go again. So, Java 1.5, they say, you see some people write hash, this is basically, right, it says, some people write terrible hash methods. That's okay, because we can hash that again, and then it's okay.
So if two things hash to the value 37, and then I hash them again, they'll be different.
Right. Because this is deterministic, right? Because you want hash to be deterministic. So 37, blah, whatever. Okay, it gives you 3. Okay, right? 37 again, 3. 37 again, 3. You're not doing anything. It's like you're coping over the fact that you have a poor hash method, and okay, so now you get linear search, maybe. Oh, but it's optimized. Right? No, optimized linear search, no, I want all of one, and this is not, but it gets better because, remember, the shift distances in this function were chosen as a result of an automated search over the entire for-search dimensional space. Which is why, in Java 1.6, they changed it again.
And it's still not great.
No. But it's different, right? So now it's, I don't know, some other space. Someone found a way to choose 37s to hash to 3 and 4. I don't know.
So what does everybody else do?
I'll get to that before I forget. Java 1.6, and then they say, This is good, this new approach, because the default collisions at the load factor is set to no more than 8. No, you don't want a wave collisions. So, this is what typically happens a lot. The wonderful multiplicative hash function, where essentially you get linearity. I mean, okay, look, so side comment. If you look at the Horner rule of evaluation of polynomials, you're going to find that this is essentially that. So if you're interested in that, take a look, it's wonderful. But basically what happens is the following. Let's say you're doing a string hash, right? So you start with some initial value, let's say the size. Some people put 0 there, right? And so that means that all of this is 0 times whatever, okay, so that does nothing. And if you're hashing a bunch of zeros, then this does nothing. So you shouldn't do that. Side comment, we did start a while ago a hashing mailing list, and this is why apparently more hash does not suffer this problem, because the guy said, hey, I have this thing, what do you guys think? We pointed out, maybe you don't want to start with an initial value that is a no-up. This is good, right? This is great. Do not push your luck. And then someone has to choose a magic here, value for a multiplication, and then there's a bit and to cut down the bit so you don't go to large integers, and then there's this addition here. Some people use bit XOR, I don't know, longer selector. And the problem with this is that, look, it's very easy to get carried away. This happens. This is a list of factors, right? So we start with K&R's digital method. Now, in K&R's credit, it's very important to note that they pointed out that they used the digital method for selecting those factors. The digital method being they used the 2 fingers on the 1 and 3 numbers, like this. Right? That tells you immediately, there's no guarantees. Don't trust. Doesn't matter, because that's the factor that Java chose, and that means that even with 2 character strings, you can still get collisions, even if you hash all the characters. Just 2 characters are enough. Why? Because this thing is not big enough, right?
And so most of these are small. So what's the problem with small numbers, small multipliers?
I don't know, they look cute, I don't know. And sometimes it's funny, right? So okay, fine, you get a bit shift in here, and so it's not a multiplication. Or you get this. How do you get this? How do you get this in integer arithmetic? You shift to the left, and you add whatever, shift to the right, 2, and now you divide by 4, and that's how you get 32 and a quarter. Apparently it's better, but it's still small, and this is another one, and so on. So really, you need biggish numbers if you're going to use it this way, so you don't run immediately into collisions. This is the number that Michael van der Wulk suggested. But you see what's happening? Beyond a certain number, all of them behave more or less the same. So really, if you want your own hash function, just go there, like many other people, and claim your number in the integer list, and then you can be published in integer. That's great. Oh, and then you run into this type of things. What do you think? What do you think about this? What's happening here? This is real code, huh?
Yeah. Found in the wild.
That's right. What's going on in there? No, seriously, it's not complicated. Take a look. What do you think? Some people are laughing already.
Yes, but what does this function actually do?
Returning 1, 2, 3, 4, 5.
Yes.
Yes, it's constant.
Returns 1, 2, 3, 4, 5.
Fascinating. So, yes, test. Do not believe that because it looks imposing and nasty, like, oh, look, big selector, and it has XOR in it. It must be an extreme hashing that we're doing here. So, right? And look, big XOR and more hash, that must be great. You gotta test. And I tell you, right, it sounds funny, right? No, haha. It's gonna happen to everybody, we're all human. Okay? So this is why you gotta test. To avoid releasing these things into the open for other people to find. You want to find this yourself, not others.
So you don't want them in the wild, they're non-native species. And
yeah, and then they multiply, right? Because
they will take over your hash table.
Yeah, but it's not all bad.
So here it's time for some examples of things that we've actually done that were custom hash tables. So for GemBuilder for Smalltalk, there's a thing called the server map. It maps, it has special requirements. It maps 1 key to 2 values. And these values are weak, although the key is strongly held. But sometimes they need to be strong. So it has to go strong, weak, okay? So that's kind of special requirements. And there's also some more requirements. We have the keys are integers between the range of 1 to 2 to the 40th, because these are GemStone object IDs, and that's the range of GemStone object IDs. They are typically on the lower end of that range, however, because we don't have anybody that's actually put 2 to the 40th objects in their object repository yet. And we do tend to allocate object IDs from the bottom. I mean, they're kind of scrambled around, but they have a tendency to go from the bottom. This particular collection tends to have up to about 2 million keys in it. In running circumstances, we'll get up to about 100,000 updates per second, insertions mostly, and on garbage collect, when the weak things are garbage collected and there are removals, and it can get a few 100,000 lookups a second. So we could have wrapped 2 existing weak value dictionaries with a duplicated key, and then to keep them strong, put an array in there, and I copy it into an array to keep it strong, and then throw the array away when I want it to be weak. But, given how weird this thing is, it seemed reasonable, and how often, how high the value of how heavily it's used, it seemed reasonable to build a custom thing. So here's how I built it. So I didn't want to deal in large integers, because then I profiled this application, and one of the really nasty factors in this application was object creation. So I didn't want to avoid creating large integer instances, let alone the slowness of math with large integers. So this 2 to the 40th number, it comes in as a byte array, and then I have to interpret it. So it doesn't come in as an integer. So what I do is I split the bytes up. So I take 3 bytes, and I get 2 to the 24th, and I take the other 2 bytes and get 2 to the 16th. So what I do is I have an array that's indexed by this 2 to the 16th, and then I have a hash table for each one of those. So now, I have to go through a little more. I have to look into here, and then to find the right hash table, and then do a probe into the correct hash table. But with numbers this big, that's probably still a win. This particular example, you see only the first 3 are populated out of a possible 64,000, and that's because this particular, the particular repository that this would be representing probably only contains maybe 40 million objects, which gives you a little bit of idea how big GemStone could possibly scale. If this is 40 million, it's 3 out of 64,000. But let's take a look at what one of the hash tables look like, since that's what we're looking at. So here's a bit of the hash table. The way it's stored is key, value, value, key, value, value, and so on. And the whole thing is a weak array. Now, I said that the keys were supposed to be strong, and the values are supposed to be weak, except when they're not. And the way I can get away with this is that the key is a small integer. So even if the array is a weak array, the small integer is never going to be collected. This is VisualWorks, by the way. This is 32-bit VisualWorks. So so in VisualWorks, as in most Smalltalks, the small integers cannot be garbage collected. So that works out, and I make the whole array weak, and it turns out that VisualWorks has the ability to switch an individual object's weakness. You can switch the weakness on and off. So I use that, and it's pretty fast if you're careful. There are consequences to switching the weakness of the object at exactly the wrong point in the garbage collection cycle. Performance, it's correct. It behaves correctly now. But there was a bug at first, and this guy fixed it in the VM. But now it works very, very nicely, but there are certain, if you switch the weakness at certain points in the garbage collection cycle, the garbage collector has to do a lot of work, and it slows down terribly. So early on in implementing this, I made a terrible fail, and I found it in testing, right? Testing. Which is, I got about 1 million elements into this thing. And my test was consuming CPU, and it wasn't finishing, and I didn't know why. So I break into it, and I take a look and see what happens. And I've got about 1 million elements in one of these, one hash table, in a single hash table. And I look at what's actually in the hash table. So I've got about 2 million slots in the hash table. And what I've got is a single clump of 1 million objects and a single clump of 1 million free spaces. And this is because I was using the low order 24 bits of the object identifier from GemStone directly as the index into the table. And it turns out that those things have a pattern. They're not random numbers. So, they tend to go, 5, 4, 3, 2, 1, 27, 26, 24. Anyway, they interacted terribly with that. So I ended up using hash multiply, and then mod s, and it just works lovely now. I didn't ever actually let the test finish the first time, but it goes so fast now. I'm, very conservatively, this is a 100,000 times speed up just by adding hash multiply to that.
Which cost extra work.
Which cost extra work and saved a lot. So
yes, and this is hardly the only case. A while ago, I was working at someone, and there's this. Where's this guy? I don't know. Maybe later I can hint at it. But anyway, so there were these points that were really funny because they define equality this way, right? So xy is equal to xy, but xy is also equal to yx. Which means that the usual trick of making a hash function depend on the order in which you hash things to kill linearity doesn't work. Which means now your hash function has to commute. And what did they do? X plus y. And this is bad because the points were in the square -20, -20 to 2020. So now you can imagine that, well, first all the diagonals hash to the same, right? That's bad. And then, well, 1, 2 hashes the same to 1. And 1, 2. So everything collides, complete disaster, right? And it's wonderful, right? Because also 1, 2 also collides with 0, 3. And -1, 4. -2, 5, and all the symmetric disaster, right? So the request was that this thing I was taking half an hour, that was the last thing I had to do before I could go to bed, would stop taking so much time. Half an hour. So I break into the provider, 90% linear search in a dictionary. So I said, well, yeah, this hash function is an hour. So I replaced this thing here, with this thing. Which if you pay attention, you'll see that this bit is a commutative hash function. And this thing is also a commutative hash function. And the addition of two commutative things also commutes. So that's great. But both of those commutative hash functions have collision in different places. To try to get the collision count down, right? It was horrible. Now, this hash function takes 5 times more computing time to run. So look, I just put in something that is 5 times slower. What do you think happened?
You got fired?
No, the customers were super happy because I gave them half an hour of sleep every day. Because what happened was that this thing took 20 extra time and this took 1 extra time. Half an hour became 90 seconds. And hashing was gone from the profiler. I tried to profile to see if hashing was there still. There's nothing. So there you see, right? You increase the quality of this, and now you get O of 1 as opposed to O of n. Did I hear some yes?
Have you tried to make it even
better? I'm no longer there. Sometimes I wish. For a long time, I thought of this particular workplace as a nice place to have a vacation, actually, because I had so much fun. But yeah, I really did. But there are ways, for instance, what you can do, since this is the 20 by 20 point square, so there are 1,681 points in there. Everybody knows that 21 square is 1,681.
But Andres, I lost you for just...
Yeah, but hang on, let me answer to him and then I take care of it. So what you could do is, well, so you have 1,681 points, right? And only say the top of the diagonal. The diagonal and the top are different according to this equality, right? So you can number them, right? And it turns out it's the sum of 1, 2, 3, 4, 5, 6, 7, yeah, well, Gauss. Right? And so it's n times n plus 1 divided by 2, great, no collisions. But watch out, because now you're introducing a perfect hash function that may be non-random, so you gotta be careful. Yes?
No, I don't understand. So you get collisions, in the original one, you got collisions along lines in the plane which are straight lines, that is first order, right? But now you also get collisions just along elliptical sections, no? So is
but
that
as you
why
see,
why is it all of one?
Because what happens is that you get much closer to O of 1. Actually, the collision rate for this is about 2. So I would submit that 2 is close enough to 1 to qualify as O of 1. And I don't know.
We're sufficiently large.
See, my fingers are close by, so that's okay. And so what I think you're seeing is that, yes, they have different collision shapes, but also this thing and this thing collide in different places. So and now you get less of a mess.
Yeah, and the important part is, the hash table disappeared from the profile length. Therefore, even if it's fun to come up with a better one, for engineering purposes, it's quite good enough.
Yeah, what are you going to get? Oh, look, it was taking 0.01%. I spent 2 weeks of engineering time optimizing nothing. I did no work. So here's another interesting thing. So sometimes I do number crunching for fun. And I had a test where there was a computing task of finding duplicate path pairs. I'm not going to describe what they are, but basically each of them is 16 bytes, and there's a struct with like 3, 4 fields, whatever. And the idea is to find duplicates. Well, you can find duplicates with a set, right? Because you take each of those, you put it through a hash function, you send it to a table, and now you're not doing linear search like the previous guy before. And that's great, except that, hey, if I put all the pairs, this happens. And I want to increase this number to like 2 to the 40, and hey, memory, right? And so, what to do? Well, one of the particular things that you do when you do this number crunch is that you start noticing patterns in data. And it turns out that if there were to be duplicates, for the most part, they would happen within the last 11,000, 20,000 pairs. So really, you don't need to keep everything, right? Because as you keep along, if you go to pair 1 million, you only need to keep about, let's say, to 900,000 or 800,000. If you go to 1 billion, you only need to do to like go 980 million, blah, blah, whatever. And so here's what you can do. So you make a smaller table, right? And every time it gets so big, because of course you set the size to cover the duplicate boundary that you need, each time it fills, you mix it with generational scavenging. And so you go through the table, not in hashing order, but in linear order, because then caches and all that, right? And you scavenge from here what you need, and you throw it there, and you continue the computation there, and this fills up. You come back here, which is empty now, and so on and so on. And this is great, because now, for instance, this is an actual test, you can increase this to that, and this is the memory you use. And by the way, all of that fits now in CPU cache, way faster. And I thought this is great because it shows really the value of combining this type of approaches with memory management.
Okay, and the last example, the GPS client map, which is sort of the inverse of the one I talked about before. So this one, it's an identity dictionary. It has the same kind of things for speed and size. This one's a little different. It's in 32-bit VW again. The key is supposed to be weak, the value is supposed to be strong, always, fortunately. And but in 32-bit VW, there are only 2 to the 14th identity hash values. They range from 1 to 16383. So what I did was I built a table with exactly 16383 buckets, always. Because typically this thing goes from like 10,000 to 2 million, right? So if I pre-allocate all 16K buckets, it's fine. And here's the structure of a bucket. We have keys in a weak dictionary, and we have the values in the strong bucket object, and we have a named instance variable that points to the keys array. And so we do get a linear search through there, and this one did use a linked free list for keeping track of the free things, because the number, when you get 2 million objects in a thing where you only have 16K buckets, the bucket size itself gets pretty big. So there's a whole strategy for growing buckets and linking the free list in buckets and whatever. But this, that gives you an idea of another way to do things when you have certain constraints. So we're coming on down to the end. I know that a lot of you are getting restless, but we do have a rather incomplete list of ways to fail.
Yes. Become is like the number one example to start breaking stuff. Every time you think you got something to work, well, try become and call me later. And so, for instance, hey, norm one way become Dale.
No!
Sorry, norm. And the problem with one way become is like this mass replacement. So you just now put Dale in the wrong slot. So first of all, now you have a problem. Where did the norm go? And second of all, now you have 2 Dales. Try debugging that, why that behaves weird later. It's not fun. So don't do that.
No.
And at least become, right, works well with identity hash, because usually it swaps them. So if you have an identity collection, you're fine. But if you don't, now you have even worse problems, right? Because now norm is misplaced and Dale is misplaced.
We can still find
does not
James.
work. Oh yeah, right. Yeah, it's just nasty. And so here's another one. You can, hey, let's grab the key and mutate, right? So that works. And if you mutate the key, now it doesn't work. You see, right? It's the same thing as a become, but you can do a put or something, and now it's all broken. Here's another wonderful thing that you can do. None of this, by default, is thread safe. Nothing is mutex. So if you happen to have a case in which you start an output, say, and in the middle of the output now you get a process switch, and the process that comes in decides to do another output, now this output is running while this one has the collection in a consistent state, bye. All that poor hash collection becomes corrupted. Again, try debugging that, it's not fun. Here's another one that is interesting. You notice how equality likes to be helpful. This means that whoever has to implement hash doesn't have a nice job now, right? Because all these hashes have to be the same. So those hashes have to be the same, and these hashes have to be the same, right? What happens when someone says 1 to 10 billion? Ouch, right? That hurts. Here's another one that's fascinating. People claim that this is possible. This is impossible. Mathematically impossible. That doesn't work. But regardless, right? You want equal. Anyway, and here's, so you want floating point? Here's another one. Nan is, by definition, never equal to nan. So you cannot use nan as a key in a hash collection, because you'll never find it.
And the only object that's not equal to itself.
That's right. And by the way, if you want, look at the spec. You can't even compare the bits, because there's several billion bit representations of nan. And you know where this is going, right? Check this out. So you start here, and you start saying, hey, what about our number types? Hey, decimal floating point, and scale decimal, and different precision here. Is it float or is it double? Or you take the fraction and then you convert to double precision. And then you take an integer that doesn't fit completely in the mantissa, you convert to floating point, and it's still equal, right? What about 10 to the 400 is equal to infinity? Right? They're equal, the hashes must be the same. And this already breaks the excluded middle, because because you would expect that, okay, they are not equal, so they must compare for less than or greater than. No, neither. What does this even mean? This is nasty. And excessive reliance on equals means that the hash methods grow extremely complicated, and because of that, inefficient and suboptimal. So careful what you wish for. And finally, please don't do this. You see what's happening here?
Yes. I would say linear search.
Yes.
Back to our old friend order of n, if you remember that from about 3 hours ago.
Don't do hashing in reverse.
Okay, so we've given you lots of ways to fail and some ideas for how to possibly succeed. So just a few final thoughts, and then we will release you from your servitude.
Maybe.
Okay, so for your hash function, we've shown hash function quality, even distribution, relatively small number of collisions, getting down towards that number for the ideal random number generator for collisions, matters more than the speed of the hash function itself, because the speed of your hash table will be paid for, will pay for that speed in a slower hash function. And quality does not equal complexity. There are many good hash functions that are very simple, and there are many bad functions that are very complicated. And the other combinations as well, but, all told, pick a good one, make it as simple as you can. Remember that the hash method is only half of the hash function, that, you need to look at the behavior. If you're using a standard collection in Smalltalk, then it's going to take it modulo the size of the table, which will be a prime. If you're developing your own system from hash, from scratch, like I did with the one that's 16383, then you're not going to be taking the modulo number, but you need to know what that entire hash function does. And last but not least, once again, do not believe authorities, including us, please.
Or yourself.
Test. Yeah, don't believe your instincts, don't believe what you read on the internet, don't believe this video that you might find on the internet. Test.
Test yourself with your data.
Any questions? Yes?
So, I'm lazy. So,
What?
So,
No, sorry.
so I like to write code that runs much more. So I write tools so they do the work for me. So the thing is, I pass most of the time. So you said, okay, hash function is is two things, and I pass most of my time just writing one part of it, and the other one I never touch it, and I ignore it. So and they come with the collections that I use all the time. So what do you think? Would it make sense that actually we write benchmarks or a framework that actually could benchmark my objects and my hash method for me? So I can only write some generator for objects.
So a good idea. So the question is whether it's a good idea to write a test framework that tests hash methods.
Yeah, I have a thought or two on that. Yes, I think it's an excellent idea.
Has anyone ever written such a thing?
But
Yes, actually, yes. When I did hashing for VisualWorks, I tested 300 hash methods against 100 standardized datasets, and it's an eye-opener. All the random wisdom and because this name was this author was written in a piece of parchment, and the parchment was lined in gold. No, enough. Look, the number's done. Thank you. I'm done. And way better, way better. In fact, if you're interested in working on that, let me know. We can chat. Next. Oh, yes.
Have you tried when you have the bucket? Have you tried making the bucket again a hash collection, but with a different S? Same. Of course, it's the same hash function, but different S, because the probability of collision will be now the product of the probability of collision in both with both models. So, and this decreases the probability a lot.
So the question is, if I understand it right, is whether changing the size of the hash table with the same hash method might improve or
No.
Okay.
No, you have the collision. Then you put a bucket. In the bucket, you mentioned the linear and the array of the link. Both of them are linear.
Right.
What if we put again there? If you have tried that was my question. A hash collection again, same hash function.
Like two-level open hashing.
Okay, so
The function's a bucket.
So the suggestion is that we might be able to put in a bucket another hashed collection for the bucket, which uses the same hash function
but
with a different S. Okay,
so this will reduce the probability of collision.
So first of all, I have to say, and this is very important, right? The hash method is not the hash function, so if you change S, you have changed the hash function. Okay, but if you use the same hash method, then in some cases you might be able to get an improvement, but I would say that in those cases it was a very bad collection in the first place.
Yeah.
Because really you ought to be able to get buckets that are small enough that you just don't need to do that. Because a linear search of up to about 10, 15, 20 items is just as fast as a hashed collection. It's only when they get bigger that you really need a hashed collection. Anybody else?
There's another thing about that question. If you put like hash list on the bucket, you have now a huge bucket because that needs to be a huge list, but are mostly empty sometimes. So memory consumption just
Right.
explode.
Could happen.
Yep.
Do we get to go home now?
Do we go? Or do you want the extra
Have
slides?
dinner?